Previously, when we were looking at hypothesis testing, we looked at the scenario where we had one population, we were interested in the population mean, and then consequently by this testing tree for the course, we were going to be doing the one sample z-test, right? But there's this little t in here too. And in what cases do we use a t-test? Okay, because it's apparently the same sort of process that we have to follow, using one population, being interested in the population mean. So let's take a look at those scenarios where we would need a t-test instead of a z-test. So when we were looking at the z-test, remember, we had these three conditions for the z-test, right? We had to have the observations being IID, independent and identically distributed, and then remember that's typically satisfied by having an SRS, and then the characteristic that we're looking at must be normally distributed. And then the last big condition that we introduced was that the sigma, the population standard deviation, is known and finite. But, I mean, that's a parameter, right? How often do we know parameters for population? Populations are typically pretty large, right? So, that condition I haven't read because it's hard to satisfy. And then consequently, if we don't have it, then we can't use the z-test. So then we need to do something else. And the t-test comes in, or the t procedures, I'm going to say, because we're going to talk about confidence intervals and hypothesis testing. The t procedures allow for more wiggle room. Okay, effectively, the t procedures are at least the first two are the same from the z-test to the t-test. Okay, so we still have to have IID observations. We have to have normally distributed the characteristic must be normally distributed in the population. That we have to discuss further in video 17-5. But then the big thing here is that the condition number 3 changes from sigma being known to unknown. So if we do not know the population standard deviation, that's where we have to do the t procedures. Okay, and when we use the t procedures, that actually changes the distribution, and that's a common thing in statistics. When we change when we change the test or the procedures we're going to be using, we end up changing the distribution. So the z-test corresponded to the standard normal distribution, right? Because we had z-scores and went on with our life there. When we look at t procedures, that follows the t distribution. And so you're going to see that it has some characteristics that are very similar to the standard normal distribution, the z distribution. It's still symmetric, unimodal, bell-shaped. And so here we see different t distributions. Okay, so the standard normal is in green. And the other ones, so we see there's, this purple one. If there's 1 degree of freedom, we haven't even talked about what that is. There's another one with 2 degrees of freedom, 10 degrees of freedom, and then there's the z distribution. Okay, but still a t distribution has that symmetric, unimodal, bell-shaped characteristic associated to it. Its mean is still 0, in line with the standard normal distribution. The only thing the biggest thing that changes here is that the t distribution has what we call heavier tails, meaning that as we look to the values further away from the mean, right, the tails here, which would be this, maybe I'll put it in red, this region over here and this region over here, those have greater probability, meaning, and remember, probabilities with curves are measured as areas, so there's more area underneath the t distribution in its tails than compared to the green curve, that standard normal distribution. That's what heavier tails means. Okay, and then as a consequence, because there's more probability in those tails, the spread of the t distribution is not the same as the spread. So if we compare standard deviations, for instance, the standard deviation for the t distribution is going to be greater than that of the standard normal. And then there's this degrees of freedom idea, and we'll get more into that as we get into the chi-square distribution. But right now, degrees of freedom, we say that is n-1. Okay, I don't want to say too much more on that because that'll spoil our story when we get to chapter 20 and 21, or 21 and 22. But anyway, t distribution, very, very similar. That's the big idea. Because it is so similar, if we need to know probabilities or anything, it's very much in line with what we have done before. So with z-procedures, remember, if we're calculating a probability, we would do norm.dist, 1 minus norm.dist, 2 times 1 minus norm.dist, etc. T-procedures, very, very similar, except they have their own different things. We don't need to remember 1 minus or whatever. If we're just going to the left, it would be t.dist. To the right, it would be t.dist.rt, and then t.dist.2t if we have a two-sided test. And then, should we need to know, like, the certain, so if we want to know the x value and we are given the probability, that's where we'd have to do the norm.inv, and the t-distribution has the same functionality built in. Okay? So, here, this is just a quick test with what you would use to find each of these things. So we want a value of t, and then we want 2 probabilities. I want you to pause the video, see if you can identify which of the 4 commands here you would use for each one of these, and see if you can figure out the syntax. Okay. Remember, degrees of freedom is in here, so you have one piece of the puzzle already done for you. And here are the commands that you would use. Okay, now I just want to take a moment and visualize each of these on the curves above. So for example, the first one I'll maybe visualize here in red. So we want to find a place on the curve, so this t value, such that to the right of it is 60% of the area. Okay, so if I need to look at this curve, right, because that has the 10 degrees of freedom, that should be with the, let's try it with that one. Okay, so we wanted to place on the curve such that that 60% of the area is to the right, so I know at the 0 mark is the 50 percentile, and then maybe somewhere, I don't know, around here, I'm going to say, so I'm looking for this spot on here. Okay, in the other ones, so the last one was, or the second one was, a place on the curve such that t is not equal to 0.2, so 0.2 is right here, and then I need to consider the symmetric area, so it'd be something like this, and then to the right, and then similarly to the left. Okay, and the last one I can do here, it's going to be very, very tiny, but from 0.1 to negative 0.1, that would be this region here. And then remember, since I'm doing a between one, it's easiest just to do the upper one minus the lower one. Okay, so just to give you an idea of what these things look like on the curve. Okay, but now the more important thing is, can we calculate them? Let's go into Excel and do that. Alright, and here we go. We're going to go into Excel and do t.inv, and then 0.4 and 10. Okay, so that's the first one, negative 0.26, and that was, I maybe took a little liberty with that one and drawing it, but there we go. Second one, we had to do t.dist.2t, and then for our x, 0.2, and then 10. Boom, there we go, 84%. And then for the third one, it was t.dist of 0.1, 10, true, minus t.dist of negative 0.1, 10, and true. And there we go. Okay, so I can copy those 3 answers down into the notes here, but effectively, just keep in mind, as you change tests, you change distributions, and then change how you calculate probabilities. Okay, and for us, we're still looking at one population. We're still interested in the population mean. It's just now we do not have the standard deviation the population standard deviation is known, so that's when we have to do the t-test.